The concept of photovoltaic is to use solar panels made of silicon to produce electricity using sunlight. Silicon is one of the most abundant elements on Earth, since it can be found in sand and dust. It has a very interesting property: its electrons start to move when exposed to light. It is known as the photovoltaic effect. But how does it work? Well, basically, a photon from the sunlight knocks loose an electron from the silicon that migrates then to these tiny conductors. It causes a flow of electrons which, by definition, is a current.
This video I'm going to go ahead and show you how to hook up the tab solar cells into long strings so we can make a solar panel out of this. In brief, flip over the panel like that. The white areas are going to be the positive connections and the tabbing wire is always the negative part of the solar cell. Or think of it as like a solar battery. And you just line them up. Slip another one like that. Okay, so I cut those ends down. So these are the negative from this panel. This is the positive from this panel. And all you have to do now is take this bus wire, which is just a fat piece of the same type of wire, flatten it out, and we're going to solder it straight across, like that. We just have to solder here, 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 and here. Okay, and here's a close-up on the bus wire from the negative and negative to the positive and positive.
What I'd like to start with is solar panels, photovoltaic panels, which we have here, and these are oriented towards the sun to capture the sun's energy. That energy is created by the sun and is transferred through the panels into electrical energy, so we have an energy transformation going on there. That energy comes down through some wires, and we have some various parts here, including disconnects, fuses, circuit breaker boxes that are important. We want to do things safe by codes and standards. Here we have what's called a charge controller, which is a device that is common if you're using batteries. If you're having batteries as battery backup, we want a charge controller so that we can control the level of charge in the battery and also the level of discharge. Through that we go to a disconnect, a switch, and then we have in here we have our batteries. These are what's called deep cycle batteries, which are special batteries for deep charging and discharging. Regular old car batteries are not going to work for us. So these are important concept if we're using batteries in our system. From there, we go to what's called an inverter. And an inverter takes the DC, what's called direct current, which is supplied from the batteries, from the panels, so it's DC form of energy, and it converts it to AC, alternating currents, which is in the form that most homes appliances use. They use AC electricity. We go through a typical disconnect, which is generally fused. It's an on-off switch, okay? From there, we go to a distribution center, your fuse box. Most houses will have one of these that have your breaker boxes in it. So here I have two breakers that distribute the power to various parts of my simulated home.
Suppose you wanted to move a large log. That would take energy. Where could you get the energy to do it? One place, of course, is from your own muscles. You could supply the energy to push the log. Or someone else could supply the energy. Then the energy would come from someone else's muscles. Or you could use a machine, like this bulldozer. Then you'd be getting the energy from gasoline. Or you could even use an electric motor. Then the energy to move the log would come from electricity. But let's say you didn't have a friend to help you. And let's say, at least for now, that there weren't any machines around that use gasoline or electricity. Then where could you get the energy to move the log? You could still use your muscles, of course, or the muscles of other animals. But are there still other things around you that might have energy that you could use? Well, here's a small rock. Suppose you wanted to crack it in two. That would take energy. Where could that energy come from? Suppose this happens. The energy to break the rock in two came from the large rock that fell. But wait a minute. There is energy in a rock? How can that be? It doesn't look like there's energy in the rock now. But there was when it fell. What's going on here? The answer is that when the rock was falling, it had a special kind of energy called kinetic energy. All that really means is that it was moving. And because it had kinetic energy, it was able to apply a force to something else by falling on it.
Potential energy we've already seen before because there are different types of potential energy. We have seen potential energy as gravitational potential energy. You lift an object up and you've given it gravitational potential energy. But there are other types, okay? And one of those types is electrical potential energy. Electric fields can give charges different amounts of energy, and we're going to see that there is potential energy related to electricity. Because charges have energy to them, right? You separate them, they might want to pull together, you bring them closer, they might want to push apart. There's energy involved with that. And let's see how. We're going to look at an equation, and this equation, again, we won't actually do any calculations with, but it will help us explain the concept of electric potential energy. So this is the equation that we're not going to use, but we'll use it in the sense of explaining the concept, not in a calculation. So U sub E is equal to QV. The U in this case is potential energy. We used PE before, but another common variable to use is U. So U sub E, the U indicates its potential energy, the E indicates its electrical potential energy. So we could just say PE sub E, but that's why we use U sub E. It looks cleaner. And that's equal to QV. Well, Q, like normal, is charge. And then V, we just saw, was electric potential, also known as voltage. So you'll see that electric potential energy, U sub E, is not the same as electric potential. It is not equal to V. It's related though, okay, through QV. So it's related, very similar, but not the same thing.
Electrical energy is different from electrical power because electrical energy gives us how much energy we've used or we're using as opposed to how much electrical energy we have, okay? There's a simple equation that gives us electrical energy. It says electrical energy equals kilowatts times hours, okay? Because the unit of electrical energy is the kilowatt hour, okay? And we're just
Power is a measure of how quickly energy is transferred, and it's measured in watts. The more energy that is transferred in a certain time, the greater the power. A 100 watt light bulb transfers more electrical energy each second than a 60 watt light bulb. Like the power of an electrical appliance by knowing the current that flows through it and the potential difference across it. You simply multiply the current in amps by the potential difference in volts. Well, that's simply 7.5 watts. Fuses play an important role in making sure our appliances don't fry when a surge of electricity flows through them. By rearranging the equation P equals IV, we can work out the best fuse to use.
Okay, this is your basic circuit for a series circuit. That's a battery symbol. Come out of your battery to a resistor. A little sloppy here. Another resistor. Another resistor. Okay, that's your basic series circuit. This is E. Make it 12 volts DC. R1, R2, R3. And we'll say this one's 10 ohms, this one's 10 ohms, this one's 10 ohms. Okay, now, in order to find your total resistance, which is R total equals R1 plus R2 plus R3. That's your basic formula. So, in this case, R total equals 10 plus 10 plus 10. So, R total equals 30. Now, to find your amperage, your I total equals I1, which equals I2, which equals I3. In other words, your amperage is the same throughout this whole circuit. So, in this case, you call this I1, I2, and I3, which is your amperage on all three resistors. So I1 equals, okay, first of all, you got to find your voltages. Now, since you know there's three, and when all three resistors are the same, you can do it the easy way. Just say E